Good morning. Now, this is our fourth class on uh, oscillations. So, today we are going to discuss about some examples of simple harmonic oscillators. Okay, now simple harmonic oscillators means anything that executes simple harmonic motion is called a simple harmonic oscillator. Here we will discuss about two types of simple harmonic oscillators. One is simple pendulum and the other one is compound pendulum. Now, here in each of these cases, our aim is to obtain an expression for time period of oscillation. Okay, capital T. Once you get time period, you will be able to determine acceleration due to gravity, that is small letter g at the place. Okay, so this I think compound pendulum you have done in your practical sessions, that is you have found out T, and using the value of T you have found the value of g, that is acceleration due to gravity, right? So I hope you remember how you did compound pendulum experiment. And now in this class, today we discuss about simple pendulum, and in the next session we will discuss about compound pendulum. So simple pendulum I think you might have studied in your lower class. So let us begin. See, simple pendulum, it consists of a small but a heavy mass suspended from a rigid support by a non-extensible light and flexible string. So I think you got the picture. See, this is that this one is the rigid support that they are talking about, and this is rigid support. They have given the name point of suspension. Okay, then from that rigid support you are having a non-extensible light and flexible string. Okay, and now at the end of the string you have got a small but heavy mass. That small but heavy mass is called as bob. Okay, now the center of mass of the oscillating mass, that is center of mass of this bob, is called center of oscillation. Okay, now the distance between the center of suspension, that is the distance between the point O, that is center of suspension, and the center of oscillation, this one, is called the length of the pendulum and is denoted by capital letter L. Okay, hope everything is clear from this figure. Now we are going to start the experiment. For that you are making the pendulum to oscillate in a vertical plane. That is, oscillation means you are just displacing that bob from its equilibrium position. Now that oscillation is represented by this dotted line in the figure, and as I already said, let O be the center of suspension. Then let L be the length of pendulum, that is the distance between center of suspension and center of oscillation, and let M be the mass of the bob. Then at any time t, let the mass is at a point P. Let the mass be at the point P. Then it is displaced through angle theta. Now at the point P, the force acting on the mass is mg and is acting vertically down. Now the weight of that pendulum, that is mg, and the reaction force at the point of suspension, that is the weight of the bob which is mg, which is acting vertically downwards, and the reaction force at the point of suspension will produce a couple or torque. And what will that couple do? It will try to bring the pendulum back to its equilibrium position. Okay, now that torque which try to bring the pendulum back to its equilibrium position is represented by the letter tau and is given by minus mgl sin theta. Theta is the angular displacement, L is the length of pendulum, G is acceleration due to gravity, and M is the mass of bob. Okay, now what does that negative sign means? That means restoring force is directed towards the equilibrium position. That means it is opposite to the direction of increase in theta. Okay, now let capital letter I be the moment of inertia of the bob and is given by ml square. That is, moment of inertia is given by ml square. And let alpha be the angular acceleration and is given by d square theta by dt square. Okay, then the restoring force can again be expressed using another expression, that is tau equal to I alpha, moment of inertia, which is the expression we have already discussed, ml square, and acceleration alpha, which is d square theta by dt square. Now you just compare equation 16 and 17. The LHS is same. Both are expression for torque. So you can equate RHS. Then it will look like ml square d square theta by dt square is equal to minus mgl sin theta. Okay. Now cut the common factors. M and m get cancelled. L will get cancelled. So it will be L d square theta by dt square is equal to minus g sin theta. Now here for small values of theta, we assume sin theta to be 0. Sin theta to be approximately equal to theta. Okay, so the above expression will reduce to L d square theta by dt square is equal to minus g. Instead of sin theta, you can write theta, because for small values of theta, sin theta is approximately equal to theta. Now, rearrange this equation, that is L d square theta by dt square plus g theta equal to 0. Then dividing throughout with L, you will get the final expression or the equation of motion for a simple pendulum as this. Okay, now you just compare this equation with the equation of simple harmonic oscillator. What is it? D square y by dt square equal to y square omega square y equal to 0. So on comparing equation 18 and 19, in place of omega square, what you have? G by L, right? So omega will be equal to root of G by L. Now we can find the value of time period. What is it? Time period T equal to 2 pi by omega. That is equal to 2 pi by omega. What is your omega? Root G by L. This again reduces to 2 pi root L by G. That is the expression for time period of simple pendulum. Okay. Now, acceleration due to gravity will be this one. G equal to 4 pi square L by T square. How you get that? Here you know T is equal to 2 pi root L by G. Just square it. So it will be T square 4 pi square L by G. From that, G will be equal to this one, 4 pi square L by T square, equation 21. And so an experiment can be performed to measure time period of even pendulum for different values of length, and in each case you will calculate the value of L by T square, and using the average value of L by T square you can substitute that average value of L by T square in equation 21 to get the value of acceleration due to gravity G, which is what you have done in the lab in the case of simple pendulum. Similar is the experiment for you have done in the lab for compound pendulum, right? Similar is the experiment for simple pendulum also. So I hope this derivation is very easy for you to study. So please go through it today itself. This is also an important one. So an essay question. So please study it. Okay, thank you.